Hello all, a very good day. I hope everyone is safe, everyone is doing well. So in the last video we discussed about a very simple, intuitive yet effective self-supervised learning method, the RotNet based self-supervised learning, where you just need to predict the degree of rotation. And in this video, we are going to implement the RotNet logic for our custom data set. So basically I'll be showing by emulating a scenario where you will have a good amount of unlabeled data and a small amount of labeled data, and how we can, use self-supervised learning to get knowledge or the representation from this unlabeled data and help to improve our learning on this small amount of labeled data. And with a small experimentation, I already observed that, using this RotNet based logic improves my result already. As you can see, the orange curve is the result when the model was not trained with the RotNet, pre-trained with the RotNet, and the blue one is when the model was pre-trained with the RotNet. So let's get started. Well, the idea of RotNet is pretty simple. You take an image, you rotate it by some degree, and then you task the network to predict the degree of rotation. And then this becomes your self-supervised learning strategy. And in the previous video and in the paper, we saw that making the network to predict rotation somehow forces the network to learn good features and perform well on a variety of tasks. And also evident from the attention map, as shown in the paper, that the model was somehow learning the salient feature which was required to perform the task. And the authors have evaluated this approach on a number of datasets like ImageNet, CFAR, Places 205, and they use network like LXNet and network-in-network architecture. The official implementation of the RotNet paper is also provided by the author, and the link will be provided in the description as well. However, if you want to know more about the paper, you can follow the previous video. And in this video, we are going to implement not the exact but a modified version of it. So we'll just use the logic. We'll take a simple ResNet 18 model, and on a custom data set, we'll try to implement this RotNet logic. The dataset which I'll be using for the demo is the flowers dataset from Kaggle. So there are five categories of flowers: daisy, dandelion, rose, sunflower, and tulip, and the model need to predict the category of this flower. Now there is no separate test set provided. So what I did, I took 60 samples each from each of the flower category and form a test set of 300 samples. Now this test set is kept completely separate and it's used only for evaluating the final performance of the model. Now further, to emulate the scenario of learning from a good amount of unlabeled data and a small amount of labeled data, what I did was from the remaining training set, I just took 10% of samples from each of the flower category and form a small label data set, which I'll be using for training with the supervised learning. And obviously I'll do some pre-training with the RotNet based approach. So let's see how the working directory looks like. So the working directory looks as such. So I have this main parent folder called self-supervised learning, and I have multiple subfolders. So first is the config subfolder, config module. It consists of the config files, and the config files I have defined in the form of YAML. So it contains all the the parameters that you need for training or for defining your model. So it's for supervised model as well as for any config file you can put in this folder. And then I have the data loaders. So basically this has this script for creating the data loader, and then this another script where we can call the data loader directly in the main script and then use it for training or evaluation. Then the dataset folder consists of the dataset, all the images, and then the annotations, the CSV file that we'll be creating. So basically the CSV file has the file name and its label and class, so it gets easier to use in this way. Then I have this another data set. Well, I'll talk about this later. And then there's experiments folder. So it has all the name of the experiments that you do, and within every experiment you will have the tensor board files, the config files, the checkpoints. So basically it makes it cleaner to do multiple experiments because all the related stuff for that experiment will be in that respective folder. Then I have models where we'll define the model. Here I'm just defining ResNet 18, but in this script you can define other models. And then this is for the GitHub. And this SSL eval has some evaluation script like the linear evaluation and some visualization on the tensor board. So we'll see in this. And then the utils basically have some helper functions to help us in our code. Then we have these train supervised learning and train self-supervised learning, which is basically the main script to do the training. And then there are some notebooks to do the preparation for our data loader. So we'll go into this one by one. So this is the notebook, and the steps would be as such. We'll be first splitting the data into train and test. Then we'll prepare a small label data by taking 10% of it. And then we'll first do a straight supervised learning on the small label data and store the result. Then we'll do a self-supervised learning. And then on the next step, we'll do fine-tuning of the small label data by having this pre-trained model from the self-supervised and see if the self-supervised help in improving the performance, which in my experiment it did. And yeah, that's how it is. So what we'll do, first we'll see the notebook to prepare the CSV file. So when you download the Kaggle dataset, you will only get the images, but not the annotation files. So I mean, yeah, you know these folders, obviously these are 5 categories. So these are the 5 categories, but you can use directly on the go. But I prefer creating a label file with the names, like the image names and the corresponding class labels, and like this class name, so that we can use it anywhere. So yeah, that's it. Let's get started with the coding part here. So the first script that we'll see is preparing this train test CSV file, and I'm not going to just run this because I will just walk you through it. So first, you just import the libraries, then we define the paths like your parent path, and then define your image directory where it is dataset flowers. Then when you do a list directory, you will see the list of all the directories in the flowers. For us, it were 5 categories of flowers. Then we'll assign the number, like integer label, to each of these classes like daisy, dandelion, rose, sunflower. Then I'll create 2 data frame. One will have the file names and labels for the train data, another will be test data. Now as we said, we don't have a separate test set, so we'll choose 60 samples from each of the category, flower category, random samples, and we'll save them into this test data frame. So basically there are 2 loops that you can see. The first loop will be looping over the different flower category, and the second loop is to loop over all the images within that specific flower category. So when we loop, we'll list out all the images of each of the flower category, and then the label of daisy will be 0. We can see from this dictionary daisy label is 0, so that's what we are calling here. And then one more thing is I'm also creating a counter for corrupted files. If there are any file which is corrupted, we will not save them in the annotation file, we'll ignore them. And yeah, I'm just having this test list index, which will be random 60 samples for this category. So start looping over by defining a range over the number of image files, and then I'm defining a full path file name by giving this full path of image directory, the data set, in this case daisy, and the image name. I'm reading it, and if I'm not able to read, then I'm marking it as a corrupt file. And then if this ith index fall in the test list index that I have defined, then I'm putting this image file name in the test data frame, else I'm putting them in the train data frame. So running this will then give you this, that it has read how many images out of how many images. There were no corrupt images, and then you will get your list of image names and corresponding labels and classes. Now the final step, once you have saved everything or appended into the data frame, is to save the data frame as a CSV file. I am saving it as flower recognition train.csv and flower recognition test.csv. So yeah, here it is. And I would request you to run the script yourself, although I'll be uploading this, because the way I'm saving is I'm giving it full path. I'm not giving it a relative path, so it's like a hard-coded path here. So you can either run this script and create a hardcode path for yourself, or you can define your relative path. So once I have this CSV file, then let's do a quick EDA of let's see how many classes how the class is distributed. So basically I'll be importing all these libraries. I'll be defining my parent path, my image directory, and now we have created this annotation file. So the train label path and test label path would be simply the annotation folder and the name flower recognition train.csv, flower recognition test.csv. And we'll be reading this. So we'll be reading the Panda library, read CSV. And we have this dictionary of class to labels, labels to class, like from integer to name and name to integer. And then you can just print the info and you can see, how many entities, objects are there. And these are some heads. So now I'm going to plot the train data distribution. And when I plot the train data distribution, you can see that it's pretty much, not that much imbalance. It's kind of okay. The Dandelion has highest number of samples, but nonetheless, it's quite okay. And the total number of samples, I think, are around 4023 for the train. And then coming to test, that we know, we chose 60 samples from each of the categories, so total 300 samples, and this is it. So, and then we can also plot some of the samples from the data frame. So what I'm doing is I'm just randomly choosing index that I'll be using to extract the sample from this train data frame, getting the location of that index, and then I can just see is it this like the label. And same thing I can do to plot, like I have defined a range for eight samples, then I'm choosing 8 random indexes, and then I'm getting the sample, and then I'm reading it. Once I'm reading it, then I'm simply plotting it, and you can see the images here, like the daisy, sunflower, rose, etc. Now how can we create the proxy tasks? The same way, it's very simple. I'm just giving example here. Suppose I want to rotate an image by 0, 90, 180, 270, 120 and 240 degree. So basically we can use this function. So I'm just reading a random image from the data frame. I'm getting its sample location, and then sample of 0 means 0th is the file name, if you remember the data frame, and 1 will be the label names, and 2 will be the class names. So basically I'm just reading the file name here, sorry. Yeah, and then I'm rotating by the desired degree, and I'm assigning labels to each rotation, like 0 will be 0 degree will be 0, 90 degree will be 1, 120 will be 2, and so on. And once you plot, you can see like this. So this is how you can create your proxy task. Here you need not know the actual labels, but just the rotated degree will be its label. Okay, so cool. So we have just quickly done a quick short EDA. Now let's go to the important part of how can we prepare this small label data, small amount of label data. And if you remember, what I'm doing is I'll be just taking 10% of the 10% of data from each category as a small label data from the training set alone. So I have this root directory, then the image directory, and train label path. Actually I won't be using this test only because I'm taking 10% only from the training set, and test set is untouched. So this is the trained set, and then you can read with the pandas pd.read csv and train df.head. Now I'm taking 10%, so I'm just writing it 10 here. Now I create a new data frame called small label data, which will have the smaller amount of label data that we'll be using to evaluate the self-supervised learning. So what I'm doing is I am looping over 5 because there are 5 categories. So 0 is Dandelion, 1 is 0 is Daisy, 1 is Dandelion, 2 is Rose, and so on. So what I'm doing is within the data frame, I'm creating a shorter data frame by selecting the labels of only that category. So suppose if it's 0, then it will only select those samples of the 0th those samples having 0th label or the label Daisy, and then I am taking 10% of that sample, and then that 10% of sample, then I'm creating random indexes, and then I'm selecting those samples based on these indexes, and those samples which are selected, then I'm concatenating it to the small label data frame. So you can see the number of samples that are selected from each category are 70, 99, 72, 67, and 92 respectively. And the total number of samples in the small label data is around 400. And then once your small label data data frame is ready, then you can simply save it to CSV. So now I'll have three, in the annotations I'll have three CSV files, train, test, and this is the small label data CSV. Okay, so now we have everything ready. Now let's see how we can prepare the data loader from these data files. So in this video, we did some initial preparation work that will help us in training our RotNet model. And so we are all set. And in the next video, we'll be creating the data loader that will take this data set that we have and create a good data loader function that will be used for training the model. So I hope this was useful, and do give a like to the video. Share it if it's useful to others. Comment if you have anything. And till then, keep safe, keep learning, keep exploring neurons. Namaste.